So in the last section, I promised that we would look at a triprotic acid mathematically, not in terms of a titration curve, but pHs and what kind of concentrations we'd have over a period of time. And what we also will look at strengths of acids and bases. So let's talk in terms of triprotic acids first. I have a couple different types here. So the first one is sulfuric acid, and sulfuric acid is a strong acid. So its first dissociation is one arrow. So all of the H2SO4 will become H positive and HSO4 minus. You likely aren't going to be able to find a K value because it's a strong acid. Some books will call it large, and some books just won't have anything in there at all. Now, this chemical, HSO4 minus, is amphoteric. So in the first reaction, it appears to be a conjugate base, but in this context, it's a weak acid. And weak acids have a K value associated with it. In this case, 1.3 times 10 to the second. So some of the HSO4 minus dissociates into ions. Now, let's go with a different color here. The H positives that are produced in the first reaction, remember, is full left to right, so it makes a tremendous amount of H positive. This second dissociation is only partial, and so you add very little H positive compared to the initial H positive. So down here, I actually mentioned this. I mentioned this in terms of weak acids, but it's even more evident in strong acids that you're going to get almost, if not all, of the mathematical H positive from your initial dissociation. All subsequent dissociations are going to have an insignificant amount of H positive, and we'll mathematically look at this to kind of prove that's the case. But as these K values, let me backtrack. As you dissociate another H positive off of in this case, triprotic acid, the K values get smaller and smaller and smaller. So that means there's less left to right action. Okay. So if you were going to try to determine what the H positive concentration is of sulfuric acid, really you're only going to be interested in that, not in the second, or in this case there's only second. But and then for phosphoric acid, triprotic acid, it's a weak acid, so all of these are going to be equilibrium, and it's the first one that's going to be important. Keep in mind these K values because we're going to use these mathematically in a second here. Okay, so we're presented with some phosphoric acid, 5 molar, fairly concentrated, and we're going to try to figure out what's the equilibrium concentrations of everything. So what is everything? Let's erase some things here. So how much phosphoric acid? How much H positive? You technically would add all three of those H positives up. How much H2PO4? You make some, but then you use some. How much of the HPO4 minus 2? You make some and then use some. And then lastly, how much PO4 minus 3? This is going to be very small. Why? Because that K value is tremendously small. Okay, so let's jump in. So we can't do this all in one fell swoop. We have to do it in 3 parts, just like I showed in the previous slide. So the phosphoric acid can dissociate. Okay, so you have the 5 molar, minus X is approximately 5, 0 plus X is X for the H positive, 0 plus X is X for the H2PO4. We've done that, I think, a number of times. So I'm going to jump right into the equilibrium expression. X would be the, you know what, let's actually show it, because we might need these for later. 5 minus X is approximately 5. 0 plus X is X. 0 plus X is X. And when I solve for that, I get 0.19 molar. Okay. So what do we do now? Well, let's box that because we might need that. So now the H2PO4 that we produced is itself an acid. So it can dissociate. Yes, it can make some H positive, and this time it can make HPO4 minus 3. Still ICE. And our starting amount, not 5 molar, because that was for the phosphoric acid. We have 0.19 is what we produced in that first equilibrium reaction, minus X, likely 0.19. Is this a 0 here? No, it's not a 0. It's a, remember, we made 0.19. So it is still in that beaker. Plus X, probably 0.19. We'll double check these. Like when we go back and look at 0.19, did it have an impact on 5? Well, it does have a slight impact on 5. Does it a 5% rule? It's very, very close. We don't want to go into the quadratic here, so we'll leave that approximation. Now, how much? Whoops, I have minus 3 there, and that's not a minus 3, that's a minus 2. Sorry. 0 plus X is X. Okay, so this is governed by the Ka2, the second of these. So 6.2 times 10 to the negative 8th. And I think you might find that this math is fairly easy to solve for X. So X is going to equal the actual K value. So let's go back and look at that 0.19. Is it impacted by the X value? And I would say virtually 0 impact. So we were definitely okay to make those assumptions. And then we have a third equilibrium. And the HPO4 minus 2 that we produced has the ability, by the way, let's do that. Has the ability to make H positive, and this time phosphate. ICE like we did before. How much HPO4 minus 2 do we have? Remember, we made 6.2 times 10 to the negative 8th minus X. We're still going to say these assumptions. We'll see if we're on track with that. Is H positive 0? No. It's still that 0.19. Technically, 0.19 plus 6.2 times 10 to the negative 8th, but that's, on a calculator, it's going to give you 0.19. Plus X, I think we can make that assumption it's going to be 0.19. This is 0 for phosphate, and that's going to give you X. So we have a Ka3. Remember I said these Ks get smaller as we go, and this one's definitely small. Up top we got the 0.19. Up top we got the X. On the bottom we got 6.2 times 10 to the negative 8th. Solve for X, and I think this is going to be tiny. That's not a very good 9 there. Okay, so there are our X values, and I think with those values we can get all of our concentrations. By the way, let's look at the H positive. So we started off with 0 when we made 0.19. Then we're adding 0.19 plus these two X values, insignificant. So now you can see that the first equilibrium process here is going to give us practically all of our H positive. The H3PO4 is in the ballpark of 5 minus 0.19. And then we have our X values for H2PO4 minus, and our HPO4 minus 2, and our PO4 minus 3. Okay, the rest of this is non-mathematical. These are going back to kind of some Lewis dot ideas and some intermolecular force ideas and polarity ideas. So what makes something a strong acid or stronger than another a weak acid, I guess? So there's a couple things. But how well this bond connects the H and the X definitely influences the strength of the acid. Remember, strength of acid is about how much of this goes from left to right to donate H positives. So if this is easy to break, it's going to make lots of H positive. If this is very difficult to break, the HX is very difficult to break, it's not going to make hardly any H positive. So bond enthalpy is going to be very important. And then another thing that's important is how polar that bond is. So if you would have a situation that has a very, very, very positive H side and a very, very negative X side, I guess I'll put these in parentheses to designate that they're partial charges. Water could come along here and maybe fairly easily break that X away from the HX, or the oxygen part of water break the H positive away. And so the polarity has certainly a lot to play in that. Okay. Often individuals talk about this stabilizing the conjugate base. We're not going to get into a lot of details on that other than what I just mentioned there, that polarity idea. But here is a vocab that I think we need to be familiar with: oxyacids. And I think it's pretty self-explanatory, but any acid that has oxygen in it is an oxyacid. And why are we mentioning this now? Because oxygen is a tremendously electronegative atom. So remember that electronegativity is the ability to attract electrons. So the ability really to polarize that compound. Now HX, we don't know what X is. Maybe it is, in this case, ClO3. It doesn't really matter. So if I'm talking about oxyacids, we're going to put some oxygens in there. Okay. So kind of a rule of thumb, the more oxygens that the acid possesses, the more polarizable that that acid is, and so it's going to be a stronger acid. So I guess we could go with nitric acid is a strong acid, and then nitrous acid, because it doesn't have as many O's, it's not as polarizable. We can't define it as a strong acid. It's a weak acid. doesn't dissociate as easily. These have the same number of oxygens, so now it must be about another atom, and it's about the chlorine or the bromine. Okay, and we'll get into that. Well, get into it right now. Cl is more electronegative than Br is, so it's going to be more polarizable, and that acid's going to be a stronger acid. We can even talk in terms of two strong acids, which one's stronger, in this little section here. Okay, so this just shows you what I had already mentioned. The more oxygens you have, the stronger the acid is, because this is going to be very, very, very polarizable compared to down here. I don't know how I can show it as less. Maybe I'll just show it with tiny little pluses and minuses, but you get the idea that the more oxygens, the more polarized, the more electronegative atoms are attached to the acid, the more the electrons are going to be not shared equally. Here is a question that deals with the bond enthalpies. So remember that if the bond is very, very strong, it's going to be very difficult to get the H positive to pop off of there, and it's going to be a weaker acid. So this is the weakest bond, so this would be the strongest acid. It says weakest to strongest, so I guess we want to make that number 4 then. You know what, I don't really like how that kind of, let's rank them from strongest to weakest. So this is number 1 to weakest, okay? This is the strongest bond, so it's the weakest acid. And I guess, what do we got here? Like that, okay? The one below is all about the oxygens. So I'm just going to actually just go back to here, because that's basically what we have. So this is the weakest acid, and then strongest acid. I don't know if all those are on the question. Yeah, we have 4 of them. Did we have 4 of them? Yeah. Okay. Typical question, what it might look like, and like always, we have the answers. We know it's B. Let's move that down just a little bit. We got Lewis dot structures. Looks like we have 3 oxygens with this one, and looks like we have 2 oxygens with this one. Before we even get into the question, that one's going to be the strongest acid because it has the most electronegative atoms attached to it. So this side of the molecule is going to be very, very negative, and that side of the molecule is going to be very, very, when I say negative and positive, partial negative, partial positive. Getting to the question, which of the following statements identifies the stronger acid? So we've already identified it has to be HClO3, sorry, so it can't be C and D. And is it because of London dispersal forces? No, we didn't talk anything about London dispersal forces. So it must be B, just by process elimination. But what did they use here? Stabilize. And I don't really care for that term. What it means is that this side is going to be very well attached to each other because they have all those electrons. The electron density is higher there because they're all electronegative, more electronegative, I guess. But they do occasionally, textbooks or the AP folks do use this stabilize idea. But I guess we could have gotten away with not even reading B and kind of gone by process elimination there. Another question here. Looks like we already have an answer. Let's figure it out. K less than 1. What is going on here? We have little bits and we have lots. That's what K less than 1. So this acid is moving more this way than this acid is moving this way. Let me erase that. And I think we're going to be able to get the answer with that. Relative strengths of the acids. So again, that's an acid and that's an acid. Which acid's stronger? It has to be the HClO2 is stronger than that. And so that puts us down to C and D. And then remember that the relative strengths of the acids are opposite to the bases. But we could also look at this. So the HCOO minus has to be stronger than that because we're moving more right to left. And there we go.